Logistic regression. We study and model relationships between categorical response variables and continuous predictors when we run a logistic regression model. The response variable is categorical. Two levels will be binary logistic regression, and predictors could be one or more. A good example is about customer buying based on the code or not. So there are two different levels: yes or no, success or failure. So rather than establishing a relationship between the code or other factors and the success or failure, we have to estimate the probability of success. We work with odds of success in logistic regression, which is a transformation of probability. And here is how we calculate the odds of success. That will be probability of success over probability of failure. Since the total probability of success and failure together will be 100% or 1, so if we call probability of success P of x, x will be the success, that will be over 1 minus P of x. And of course, odds of failure will be the inverse of this ratio, 1 minus P of x over P of x. So for example, if probability of winning is 25% or 1 to 4, odds of winning will be 1 to 3, 1 win against 3 loss. The best way to show this relationship is a sigmoid curve. We start increasing the value of the predictor, and then we observe for example, in lower values of predictor, most of the observations are on the loss, and maybe we observe a few on the win, but then there's an area where the outcome changes. But beyond that area, most of the outcomes will be on the other side, and success. This is how we think of log of odds and a linear model in logistic regression. If you take the natural log of odds of success, that will be the natural log of the ratio of probability of success over probability of failure, which will be the difference of the natural log of numerator and natural log of denominator. A general form of log transformation to linear model will be this natural log of odds to be equal to a linear model where we have the set of x's, x1 through xn. These are the predictors in a linear model. So we go back to the equation of odds of x and probability of x and solve this equation for probability. So probability of x will be 1 over 1 plus the inverse of odds of x. So we continue to this formula, which is the natural log of odds of x will be the linear model. So odds of x will be e, or the base of the natural log, raised to the power of the summation of the constant and all those predictors with their coefficients at their optimal value. So if we replace the odds of x with probability of x, we have another transformation of the function as probability of x will be 1 over 1 plus e raised to the power of the linear model. So we will make a likelihood function. That likelihood function is a function of all probabilities of outcomes, both success and failure. The conditional probability of all outcomes happening follows the multiplication rule. So that function will be the sum product of all probabilities of success times all probabilities of failure. If you summarize that, that will be probability of success for each case raised to the power of the outcome, which will be 0 or 1, times the probability of failure to the power of the outcome of the failure. So that yi will be either 0 or 1. If the case is success, then probability of success will be itself raised to the power of 1, and then 1 minus probability of success, which is probability of failure, to the power of 1 minus 1, or 0. The result of the second term will be 1, and then we'll continue. In case of failure, then yi will be 0. So the first term will be a number raised to the power of 0. That will be 1 times probability of failure, 1 minus p of xi, raised to the power of 1 minus 0, which is 1, the same probability. So if we take the natural log of both sides, we call that log likelihood function. It will be in the following form for one predictor, simple logistic regression. If you replace the factors, that'll be yi, the outcome probability, times constant value and coefficient of predictor, plus the log Neperian natural log of the ratio we see here. General form for multiple logistic regression with multiple predictors will be the other formula. What we do here at this point is maximizing the likelihood ratio to find the set of best betas, the coefficients for the solution. We can use Excel solver to solve this problem. You can look at the supplement materials for a step-by-step solution by Excel, or use JMP. In the next video, I will explain how to use JMP, but this is a sample of the output, partial output for a simple logistic regression. Probability greater than chi-square. There's a chi-square test done for the significance of the model. It's a very small p-value that shows that the model is significant. One important number, at least we can observe here, misclassification rate, 0.29. That means about 29.5% of the results using this model misclassified. We do have the R-square of the model. Of course, calculating the R-square of logistic regression is done in a different way, about 14%. And then significance of the coefficients calculated, both for the intercept and income, which is the predictor here, is pretty high with these very small p-values. For a multiple regression model, we use fit model in JMP, which uses the binary response variable sale in Y box, and then model affects all predictors, and the personality of the model will be nominal logistic. After running the model, we can see the outcome visually on the top of the outcome, and then significance of the variables are listed, both visually and by number, p-value and log worth. That, for example, in this model, one variable is not significant at all, p-value is 0.96. One variable household is borderline 0.046 with alpha level of 5%. This will be a significant predictor, and then income, the other predictor, is pretty significant. In this model, we can see chi-square as well, the significance of the whole model. And the list of predictors we can see under parameter estimates. The same p-values are listed here as well. A very large p-value for one predictor, borderline for the other one, and very significant for one predictor, plus the intercept, which is significant.